There are objects in the universe so extreme that even calling them big feels hopelessly inadequate. TON 618 is one of them. A black hole so enormous that if you tried to compare it to anything familiar, the comparison would collapse almost immediately. It is not just large. It is the kind of large that breaks your intuition, distorts your sense of proportion, and makes entire solar systems feel small. And that is why TON 618 matters. By the end of this, you are going to understand not just the size of this object, but what that size really means, how astronomers figured it out, and why a black hole this massive changes the way you think about the universe itself. Because once you truly grasp TON 618, the cosmos stops feeling like a backdrop of stars and starts feeling like a place filled with powers almost beyond belief. If you enjoy space videos that try to make these impossible things feel clear and real, make sure to like the video and subscribe. And if you feel like joining in, leave a comment telling me where you are watching from and answer this. When you hear about something like TON 618, what hits you first? Or fear? Now, let us leave Earth behind for a while and head toward one of the most outrageous objects we know. Imagine looking into the deep universe, far beyond our galaxy, far beyond the local group, into a region of space so distant that the light reaching us began its journey billions of years ago, somewhere out there, hidden inside the brilliant glare of a quasar, and sits TON 618. How big does something have to be before the word object stops feeling useful? What does it mean for a black hole to outweigh tens of billions of suns? How can anything grow so vast without tearing apart the very system feeding it? And if TON 618 exists, is it a cosmic freak, or just one example of a universe capable of making monsters on a scale we are only beginning to understand? To get a real feel for TON 618, we need to start with something simple. A black hole is not a giant vacuum cleaner roaming space and swallowing everything in sight. It is a region where matter has been compressed so densely that gravity becomes overwhelming. There is a boundary around it called the event horizon. Cross that boundary, and there is no coming back out. Not matter, not light, not information, at least as far as classical physics goes. That much is familiar. People hear black hole, and they picture darkness, collapse, maybe a doomed spaceship spiraling inward. But black holes come in very different sizes, and TON 618 is nowhere near ordinary. It belongs to the category called supermassive black holes, the giants that sit at the centers of galaxies. Our own Milky Way has one, Sagittarius A. It is a real heavyweight by everyday standards, around 4 million times the mass of the Sun. 4 million suns crushed into one black hole sounds absurdly huge, and it is. But next to TON 618, Sagittarius A starts to look almost modest. TON 618 is estimated to have a mass of roughly 66 billion suns. That number alone is hard to absorb. 66 billion. Not million. Billion. If you line that up mentally next to the black hole in our galaxy, TON 618 is not just larger. It is larger by a factor of more than 16,000. If Sagittarius A is an astonishing central engine, TON 618 is something closer to a gravitational empire. But mass, while scientifically important, is still abstract, We say 66 billion solar masses, and unless you work with cosmic numbers all the time, your brain politely refuses to cooperate. So let us turn that mass into something more visual. A black hole's size is usually described using its Schwarzschild radius, the radius of the event horizon for a non-rotating black hole. Real black holes can spin, and that complicates the picture. But as a starting point, this gives us a useful sense of scale. For an object with the estimated mass of ton 618, the event horizon would span a diameter of roughly 390 billion kilometers, on the order of 2,600 astronomical units. An astronomical unit is the average distance between Earth and the Sun. So we are talking about an event horizon thousands of times wider than the Earth-Sun distance. That is such a large number that it still might not land, so bring it closer to home. If you placed ton 618 where our Sun is, its event horizon would not just swallow Mercury, Venus, Earth, and Mars. It would extend far beyond Jupiter, beyond Saturn, beyond Uranus, beyond Neptune, and deep into the region beyond the main planets. It would reach well past the Kuiper Belt, that distant realm of icy bodies where Pluto lives, depending on how you define the outer solar system. As you could say, the black hole itself would engulf a huge fraction of what most people think of as the Sun's planetary domain. And this is just the event horizon, not the whole gravitational influence of the object, just the point of no return. That distinction matters. If the Sun were magically replaced by a black hole of the same mass, Earth would keep orbiting almost exactly as before. Gravity at a distance depends on mass, not whether the mass is spread out or collapsed. But ton 618 is not the Sun's mass. It is 66 billion times the Sun's mass. Put that in the center of our solar system, and the familiar architecture would be obliterated. The orbital speeds, the radiation from infalling matter, the tidal environment, all of it would become a catastrophe on a scale the solar system was never built to survive. Still, the event horizon is the cleanest way to understand size. It is the black hole's edge, the silent border beyond which escape is impossible. For ton 618, that border is enormous. Light itself would take days to cross it. Think about that. Light, the fastest thing in the universe, moving almost 300,000 kilometers every second, would need more than 2 days to travel from one side of ton 618's event horizon to the other. That comparison is useful because it takes us away from a frozen diagram and into lived physical scale. A beam of light could circle Earth more than 7 times in a single second. Light reaches the Moon in about 1.3 seconds. It gets from the Sun to Earth in about 8 minutes. But to cross ton 618's event horizon, more than 2 days. The black hole is so vast that even light does not traverse it quickly. And already we should pause on something strange. Black holes are often imagined as tiny cosmic drains, compact and needle-like, with crushing gravity right at the edge. But supermassive black holes do not work quite like that. The bigger a black hole gets, the less dramatic the tidal forces at the event horizon itself can be. For a stellar mass black hole, crossing the event horizon would be disastrous. Tidal forces could stretch and compress you violently, in the famous process nicknamed spaghettification, long before you got close. But for a black hole as enormous as TON 618, the event horizon is so far from the central singularity that the gravitational gradient at the edge can be comparatively gentle. That does not mean it is safe. Nothing about TON 618 is safe. It means the horror becomes stranger. In principle, if you somehow approached a supermassive black hole like this under impossible science fiction conditions, and without being cooked by the surrounding radiation first, you might cross the event horizon without any dramatic visual marker. No wall, no crack in space, no sign saying this is the end. You would simply pass a point after which every possible future leads inward. That is one of the unsettling things about black holes. Their true danger is not that they look violent. It is that reality itself has been arranged into a trap. So where is TON 618 exactly? It is not in our galaxy. It is not anywhere near us. TON 618 is associated with a quasar, one of the brightest kinds of objects in the universe, and it lies roughly 10.4 billion light-years away. That means the light we see from it began its journey when the universe was much younger than it is now. We are not seeing TON 618 as it is today. We are seeing it as it was billions of years in the past. That detail matters because it reminds us that astronomy is not just looking far away. It is looking back in time. Every telescope is also, in a sense, a time machine. The deeper into space you look, the older the light becomes. So TON 618 appears to us from an era when galaxies were still growing, colliding, feeding their central black holes, and building the large-scale structure of the universe we see today. And TON 618 does not reveal itself as a neat black circle against a starry background. We do not see the event horizon directly the way the Event Horizon Telescope imaged the shadow of the black hole in M87 or Sagittarius A star, and a TON 618 is too distant for that kind of direct image with current technology. Instead, we know it through its quasar. A quasar is what happens when an actively feeding supermassive black hole becomes one of the brightest beacons in the cosmos. Gas and dust spiral inward, forming an accretion disk. Friction, magnetic effects, compression, and violent heating turn that infalling matter into something incandescent. The material around the black hole can glow so intensely that it outshines the entire galaxy hosting it. Not because light is escaping from inside the event horizon. It is not. The light comes from the matter just outside, from the doomed material on its way in. This is crucial. Black holes themselves are black, but the environment around them can become spectacularly bright. In TON 618's case, the quasar is astonishingly luminous, or it is one of the reasons the object drew attention in the first place. The black hole is hidden in darkness, but the feast around it announces its presence across billions of light-years. The name TON 618 sounds almost anticlimactic for something so monstrous. It comes from the Tonant-Sintler catalogue, tied to observations that originally identified the source decades ago. Early on, it was classified as what astronomers called a stellar object, because at great distances, quasars can look deceptively star-like in telescopes. But over time, as astronomers studied its spectrum, its redshift, and the tremendous energy pouring from it, its true nature became clearer. This was not a star. This was a quasar, powered by a supermassive black hole of astonishing scale. Now we arrive at an obvious question. How do astronomers know how massive TON 618 is if they cannot fly there with a scale and cannot resolve the black hole directly? The answer is one of the great strengths of modern astronomy. We infer invisible things by studying what they do to visible things. In the case of an active quasar, astronomers examine the light coming from gas moving around the black hole. They split that light into a spectrum, looking at how specific emission lines are broadened. If gas is orbiting very fast, the light from it gets spread out by the Doppler effect. Gas moving toward us shifts one way, gas moving away shifts the other, and the result is a broadened line in the spectrum. Broader lines generally mean faster orbital motion. Once you estimate how fast the gas is moving, and how far from the black hole that gas likely is, you can estimate the central mass needed to keep it bound. This is not a perfect, direct measurement. There are assumptions involved. The geometry of the gas matters, the orientation matters, the models matter, but it is a powerful method, and it has been used to estimate masses for many active galactic nuclei and quasars. For TON 618, those measurements point to an extreme result: a black hole with a mass in the tens of billions of suns. Different analyses may phrase the uncertainty slightly differently, and astronomy is always refining numbers as methods improve. But the basic conclusion remains. TON 618 is among the most massive black holes ever measured. That phrase, among the most massive, is worth keeping. Science rewards precision, not exaggeration. There may be black holes of comparable size, perhaps even larger candidates, depending on method and uncertainty. TON 618 is not important because it must hold some untouchable world record forever. It is important because it is firmly in the upper extreme, in the realm where black hole growth becomes a puzzle. How does something like this form? That question opens a much deeper story. We understand, in broad outline, how black holes can grow. A massive star collapses and forms a black hole. Or in the early universe, a direct collapse event might create a much larger seed. Over time, black holes can gain mass by accreting gas, swallowing stars, consuming clouds, and merging with other black holes during galaxy collisions. Given enough fuel and enough time, and black holes can become supermassive. But given enough time is where the problem starts to sharpen. TON 618 is seen at a great distance, which means we see it in the earlier universe. Even by that time, there had been billions of years for growth. Yes, but building a black hole up to tens of billions of solar masses is not trivial. Growth through accretion is limited by a balance point called the Eddington limit, roughly the point where outward radiation pressure from infalling, glowing matter pushes back against gravity. In simple terms, feed a black hole too aggressively, and the radiation from the hot accretion flow can start blowing material away. There is a natural speed limit, though in real systems it can be bent, exceeded for periods, or approached in messy ways. This means astronomers have to think carefully about the starting seed and the growth history. Did TON 618 begin as an unusually massive primordial seed from a direct collapse cloud? Did it spend long periods feeding at near the maximum sustainable rate? Did mergers repeatedly add mass in a rich galactic environment? Was the surrounding region of the universe especially good at delivering fuel into the center? The honest answer is that the exact biography of TON 618 is not known in detail. We do not have a cosmic surveillance recording of its life. What we do have is a strong set of physical ideas about how supermassive black holes grow. And TON 618 sits at the edge of those ideas, forcing them to work hard. And this is where black holes stop being just spectacular objects and start becoming scientific pressure tests. Extreme examples tell you whether your theories are flexible enough, complete enough, or missing something. The universe has a way of finding the weak points in human understanding and pressing on them. To see why TON 618 is so useful in that way, it helps to compare it with a few better-known black holes. Start with stellar black holes, the kind formed when very massive stars die. These usually have masses from a few times the Sun's mass up to perhaps tens of solar masses, though some detected through gravitational waves are heavier. They are compact, intense, and dramatic, but tiny compared with galactic monsters. Then, there are intermediate mass black holes, a class astronomers have searched for and studied with growing evidence, lying somewhere between stellar and supermassive. These may help bridge a formation gap, though their population and role are still being worked out. Then come supermassive black holes, millions to billions of solar masses, sitting in galactic centers. Sagittarius A is about 4 million solar masses. The black hole in M87 is around 6.5 billion solar masses. That one was historic because we imaged its shadow. 6.5 billion suns is already hard to comprehend. TON 618, at around 66 billion, is about 10 times more massive still. That comparison is useful because M87's black hole already felt like the upper end of what most people can visualize. The ring-like image made it emotionally real. It turned an abstract concept into something with shape. On a TON 618, then arrives and says, effectively, yes, that giant is impressive. Now imagine something roughly an order of magnitude more massive. And again, not just heavier, but wider in terms of event horizon. Now let us make the scale more tactile. The orbit of Neptune is about 30 astronomical units from the Sun. Pluto's average distance is closer to 39 astronomical units, though its orbit is eccentric. The Kuiper belt stretches outward beyond that. TON 618's event horizon diameter is around 2,600 astronomical units. If the Sun were replaced by TON 618, the point of no return would engulf the orbits of all the major planets and continue far, far beyond them. It would extend into the scattered outskirts of the solar neighborhood, a dark sphere with a diameter dozens of times larger than Pluto's orbit. That sounds like the black hole would become some kind of giant empty hole in space the size of a solar system. And in a sense, it would. But it is important not to picture it as a giant cosmic tunnel. The event horizon is not a solid surface. It is not a shell made of matter. It is a boundary in space-time. If you floated outside it, space might look warped, light bent, stars distorted into arcs, and strange brightness gradients. Get too close, and all paths inward become unavoidable. But there is no hard wall to collide with. This is one of the reasons black holes are so difficult for intuition. They are not merely objects. They are structures in space-time created by extreme mass energy. We describe them with sizes and edges because that is useful but the underlying reality is more subtle. TON 618 is not a giant ball of dark material sitting there like a planet. It is a region where space-time has become so deeply curved that escape from within the event horizon is impossible. Still, mass has consequences that stretch far beyond the horizon itself. Around an active black hole, the accretion disk can become a cosmic furnace. Gas falling inward does not drop straight in like water down a drain. It usually carries angular momentum, so it spirals. As it spirals, internal friction and turbulence heat it intensely. In the inner regions around supermassive black holes, temperatures can become extreme, producing ultraviolet radiation, X-rays, and enormous luminosity. Magnetic fields can also help launch jets, narrow beams of energized particles blasting out along the poles at near-light speeds in some systems. TON 618 is classified as a quasar because of that feeding brilliance. The black hole itself is dark, but the surrounding engine is dazzling. In fact, the luminosity associated with TON 618 is so huge that it can exceed the output of trillions of suns. It is difficult to overstate how astonishing that is. Imagine the combined light of an immense galaxy. Now imagine an object at the center outshining many entire galaxies. This is why quasars were once so puzzling. Before their nature was understood, astronomers were looking at distant point-like sources pouring out ridiculous amounts of energy and trying to work out what could possibly power them. The answer turned out to be accreting supermassive black holes, one of the few mechanisms in the universe efficient enough to explain that much power. Matter falling into a black hole can convert a significant fraction of its rest mass into radiation before crossing the horizon, often much more efficiently than nuclear fusion in stars. That efficiency is part of what makes quasars so bright. And when the black hole is as massive as TON 618, the whole system enters a regime of grandeur that borders on the surreal. The accretion disk itself can be vast. The broadline region, where fast-moving gas produces those spectral signatures used to estimate mass, spans enormous distances. The energetic environment around the black hole becomes a central power source visible across cosmological distances. Yet, even with all that brightness, there is an odd tension at the heart of the picture. The more luminous the quasar, the harder it may be to picture the black hole itself. The light almost hides the darkness. TON 618 is known not because we see a black silhouette, but because we see what the black hole is doing to the world around it. That is a recurring theme in astronomy. Invisible things reveal themselves through consequences. Planets tug stars. Dark matter bends light. Black holes whip gas into impossible speeds and flood space with radiation from matter doomed to vanish. The invisible writes its presence into the visible. Now, if you want to understand how big TON 618 really is, it helps to separate three different ideas that people often mix together: mass, event horizon size, and sphere of influence. Mass is straightforward in concept. TON 618 has an estimated mass of about 66 billion suns. The event horizon size translates that mass into a physical scale for the point of no return. As we have seen, the diameter is on the order of 390 billion kilometers. The sphere of influence is different. It refers to the region around the black hole where its gravity dominates the motions of stars over the influence of the surrounding galaxy. For a supermassive black hole, that region can be much larger than the event horizon, extending across significant portions of the galactic center. So when people hear TON 618 is solar system sized, they need to know what exactly is being compared. Usually it means the event horizon is comparable to, or larger than, the dimensions of the planetary region of a solar system. The black hole's gravitational influence reaches much farther, and the luminous quasar structure around it can be larger still. The central darkness is huge, but the whole active system is larger than that huge thing. Scale in astronomy often comes layered like this. There is the core object. Then there is the immediate environment. Then there is the larger system shaped by it. TON 618 is not just one giant black sphere. It is the center of an active cosmic engine spanning multiple scales, all nested inside a distant galaxy. And that galaxy itself likely has a dramatic history. We cannot narrate its exact story with confidence, but galaxies hosting powerful quasars are often systems rich in gas, interactions, and central feeding. In the early universe, galaxies merged more frequently, and black holes likely grew during those violent episodes. A merger can funnel gas inward, stir up instabilities, and deliver fresh material to the center. Every large black hole is part of a long dance of cosmic structure formation. Dark matter, halos assembling, gas cooling, stars forming, galaxies colliding, central regions collapsing, feedback pushing outward, gravity pulling inward again. When you say TON 618, you are not naming an isolated curiosity. You are naming the visible summit of an enormous invisible history. Let us slow down and imagine approaching it. From far away, you do not first see a black void the size of a solar system. You see a brilliant quasar, a point so fierce that it can outshine the galaxy around it. Against the blackness of intergalactic space, it would look less like an object and more like an electric wound in the darkness. A concentrated brilliance born from matter being annihilated, not by explosion, but by descent. Get closer, and the smooth point resolves into structure. The accretion disk blazes around the black hole, hot enough to shine across a broad range of wavelengths. If jets are present, they lance out from the poles, narrow and violent, carrying energy across enormous distances. Radiation floods the surroundings. Any ordinary matter nearby is not drifting peacefully. It is being ionized, heated, accelerated, torn apart by tides, and forced into one of the harshest environments in the universe. Approach even closer, and space-time itself becomes part of the visual drama. Light from background stars bends around the black hole. Paths that would be straight elsewhere curve here. The black hole can create a warped silhouette, a shadow larger than the event horizon, because gravity bends photon trajectories. Time, too, and it becomes strange. Relative to a distant observer, clocks near the black hole run slower. Signals redshift. Processes appear stretched. These are not visual effects added for cinematic flavor. They are consequences of general relativity. The geometry of space and time is different near a black hole. Near TON 618, that geometry is being bent on a scale that feels less like an object and more like weather in the fabric of reality. And yet there is a paradoxical calm to the edge of a giant black hole. For a very massive black hole, The event horizon is large, and tidal forces there can be relatively mild compared with those around a smaller black hole. You would still be annihilated by the environment of a quasar long before any elegant crossing scenario. The radiation would be devastating. The energetic particles would be devastating. The disk is no place for survival. But purely in terms of space-time geometry, the horizon of a black hole this immense is less of a sharp tidal cliff than popular culture often suggests. That does not make TON 618 less frightening. It makes it more alien. It is not a simple death trap with obvious edges. It is a system where unimaginable violence can coexist with deceptively smooth geometry. The universe often behaves like that. The deepest dangers do not always announce themselves in intuitive ways. Now, there is another way to appreciate TON 618's size: density. This may sound bizarre, but the average density inside a black hole's event horizon decreases as the black hole gets more massive. That does not mean the singularity, if singularity is the correct final description, is somehow fluffy. It means that if you take the total mass and divide it by the volume within the event horizon, bigger black holes can have a surprisingly low average density. For supermassive black holes, the average density can be much lower than for stellar mass ones. In some cases, it can even approach densities comparable to water or air, depending on the mass scale. This is one of those facts that sounds wrong until you understand what it means. The event horizon grows linearly with mass, but the enclosed volume grows faster as the cube of radius. So as black holes become more massive, the average density inside that horizon can drop. The black hole is not empty in any ordinary sense. General relativity is doing the heavy lifting here, not normal material packing. But the result is still deeply counterintuitive. A TON 618 is so massive and so large that the average density corresponding to the volume inside its horizon is not some unimaginable ultra-solid substance in the way people usually picture it. Again, black holes resist ordinary mental categories. They are not giant stars made of dense matter. They are not holes punched into the universe. They are not cosmic vacuum cleaners. They are regions where mass and space-time interact so extremely that our everyday language keeps failing and has to be repaired sentence by sentence. That is partly why videos like this need to slow down. A raw number does not teach you much. It shocks you for a moment, then slides off. But once you unpack the number, you begin to see what is really strange. TON 618 is not just the big black hole. It is a place where several different kinds of cosmic extremity overlap. Extreme mass, extreme luminosity, extreme distance, extreme feeding, and deep questions about cosmic growth. So let us talk more carefully about how secure these numbers are. Astronomy is not an exact measuring tape stretched across space. It is a discipline of inference, models, cross-checks, and uncertainty. For distant quasars, black hole masses are usually estimated using relationships between the luminosity of the system, the size of the broadline region, and the velocity of gas inferred from line widths. These are often called virial mass estimates. They work well enough to map a broad population, but they are not flawless. They depend on assumptions about geometry, orientation, and the physical state of the gas. So when we say TON 618, is about 66 billion solar masses, we should hear that as a best scientific estimate within a framework of evidence, not as a divine integer carved into the laws of nature. Could improved data shift the number? Yes. Could orientation effects or model refinements nudge it? Yes. But would TON 618 suddenly become a small black hole? Absolutely not. Even allowing for uncertainty, it remains one of the largest black holes known. That balance is important. Awe should not come from pretending science is more certain than it is. If anything, the real scientific picture is more impressive because it combines confidence and humility at the same time. We know enough to say this object is outrageously massive. We also know enough to admit that the exact value carries uncertainty. That is what mature understanding sounds like. And there is something else worth noticing. The fact that we can estimate the mass of a black hole 10.4 billion light-years away at all is itself extraordinary. A species that evolved on one planet around one ordinary star has learned to decode line broadening in ancient light and infer the weight of a dark engine buried in a galaxy unimaginably far away. That is not magic. It is patient observation, theory, mathematics, instrumentation, and generations of people learning how to read the universe. If you ever feel that astronomy is just pretty pictures, TON 618 is a good corrective. This is detective work performed across time and distance using photons as evidence. Now let us go back to the central question in the title. How big is TON 618 really? The shortest honest answer is this. It is a black hole with a mass around 66 billion times that of the Sun and an event horizon so large that, if placed at the center of our solar system, it would swallow all the planets and extend far beyond them. Light would need more than 2 days to cross its diameter. It sits inside a quasar so luminous that the infalling matter around it can outshine entire galaxies. And it is so distant that the light we see left when the universe was far younger. But that is still not the full answer, because really has two meanings. It means physical size, yes, but it also means significance. What kind of thing is this in the story of the universe? TON 618 is a reminder that black holes are not rare side characters. They are central players in cosmic evolution, and supermassive black holes influence star formation through feedback, shape the gas in galactic centers, and may co-evolve with the galaxies around them. The mass of a galaxy's central black hole often correlates with properties of the galactic bulge, hinting at a deep relationship between the growth of the black hole and the growth of the galaxy. We are still working out the causal details, but the connection is real. An object like TON 618 represents one extreme endpoint of that intertwined evolution. It suggests a galaxy history rich in fuel, mergers, central concentration, and sustained feeding. It is what happens when gravity spends billions of years accumulating power, and there is enough matter available to keep the process going. And if you widen the lens even further, TON 618 also belongs to the story of the early universe becoming complex. After the Big Bang, there were no galaxies, no stars, no planets, no black holes. There was hot plasma, expansion, cooling, structure slowly emerging from tiny density differences. Over time, gravity amplified those differences. Gas pooled, the first stars ignited, galaxies assembled, heavy elements were forged, black holes formed and grew. Somewhere in that enormous unfolding, a region of the universe arranged itself into a system capable of building TON 618. That is part of why objects like this feel emotionally powerful. They are not just big. They are the result of deep time acting through simple laws. Gravity pulls, matter falls, radiation pushes back, structures merge, instabilities feed centers. Repeat this long enough in the right environment, and the outcome is a quasar blazing across the universe, with a black hole at its heart large enough to humble planetary systems. There is also a sharp lesson here about human scale. On Earth, we are used to thinking in mountains, oceans, storms, nations, civilizations. Even the largest things in human experience are tiny by astronomical standards. The Sun is already beyond normal comprehension. It holds 99.8% of the mass of our solar system. Jupiter feels huge. The distance to Pluto feels huge. The Oort cloud, if we discuss it, starts to stretch the mind to its limit. But TON 618 erases those scales with unsettling ease. It takes the familiar architecture of our planetary system and turns it into something that could fit inside the dark edge of a single object. That is not a poetic exaggeration. It is a physical statement about event horizon scale. And yet, the universe is not full of TON 618-sized black holes everywhere you look. Extremes remain extreme. Most black holes are much smaller. Even most supermassive black holes are much smaller. That matters because it tells us something about rarity. The universe permits monsters, but it does not make them casually. TON 618 is not ordinary cosmic furniture. It is a high-end product of unusual growth. Rarity, though, does not make it less important. In science, rare extremes often illuminate the boundaries of what nature allows. The hottest stars, the fastest pulsars, the most massive black holes, the brightest quasars, the earliest galaxies we can find. These are not merely trophies. They are stress tests for our models. They tell us how far the universe can go under its own rules. TON 618 asks, in effect, how efficiently can a black hole grow? How early can cosmic structures become this extreme? What environments enable such feeding? How common were these conditions in the earlier universe? Are our current growth scenarios sufficient, or do we need more help from massive seeds, super Eddington accretion episodes, or merger histories more aggressive than we usually assume? These are active scientific questions. The details evolve as observations improve. New surveys, new telescopes, and better simulations continue to sharpen the picture. But TON 618 remains one of those objects that refuses to be ignored, because it sits right where astonishment meets theory. There is another subtle point that often gets lost when black holes are discussed in popular media. That a bigger does not always mean more destructive in the way people imagine. A black hole does not somehow suck in the whole universe. Gravity still follows distance. If TON 618 were somehow isolated far from you, it would not matter that it was huge. What matters physically is where you are relative to it, and what is happening around it. Space is mostly empty. Objects do not get dragged across absurd distances just because a black hole exists somewhere. The true violence of TON 618 is local and environmental. Near the center, where matter is feeding the black hole, conditions are hellish. Radiation levels are immense, orbits become extreme, tidal forces grow. But across intergalactic distances, TON 618 is not a magical cosmic drainpipe. It is a gravitational giant obeying the same laws as everything else. This is scientifically important because black holes are often exaggerated into fantasy devices. The real truth is more interesting. They are precise, elegant consequences of relativity and collapse. Their power is not mystical, it is physical. TON 618 is terrifying, not because it breaks the laws of nature, but because it follows them so completely. If we imagine the Milky Way somehow hosting TON 618 at its center instead of Sagittarius A, what would that mean? The answer is not simple, because galaxies and black holes co-evolve. A black hole that massive would imply a very different galactic structure and history. You cannot just swap them like batteries. But as a thought experiment, it helps. The central gravitational environment would be much more intense. Stellar motions in the inner galaxy would differ significantly. If the black hole were actively feeding like a quasar, the radiation environment would be transformative and potentially devastating over vast regions. Our galaxy is comparatively quiet in its center today. TON 618 represents a different mode entirely, a galaxy nucleus in overdrive. That contrast helps us appreciate something subtle about our own cosmic neighborhood. The Milky Way contains a supermassive black hole, yes, but one that is currently relatively dim. Sagittarius A is underfed compared with a quasar. It is not unleashing the kind of radiative fury associated with objects like TON 618. In that sense, our galactic center is almost calm. There are still energetic phenomena there, of course, but not the all-consuming brilliance of an active quasar engine. So TON 618 is not just larger than our central black hole. It belongs to a different emotional category of cosmic object. Our black hole is impressive. TON 618 is operatic. And because it is so far away, there is another strange comfort in that. The universe is capable of producing such extremes, but not next door. The light from TON 618 took more than 10 billion years to get here. By the time it reaches us, it arrives not as danger, but as information. We study it safely from a distance that no human scale can meaningfully picture. This is one of the gifts of astronomy. The universe shows us terrifying things in a form we can survive. Light. Now let us return once more to the image of the event horizon swallowing the solar system, because this is usually the comparison that makes people stop and feel the scale. The Sun's diameter is about 1.39 million kilometers. That already dwarfs Earth. Jupiter's orbit around the Sun is about 5.2 astronomical units. Neptune's is about 30. TON 618's event horizon diameter is around 2,600 astronomical units. That means if you drew our familiar planetary layout around it, the whole inner solar system would disappear almost absurdly close to the center. Even the outer planets would be nowhere near safety. The point of no return would sit so far out that many diagrams would have to be completely rescaled just to fit it on screen. And if you then ask what lies at the center of that enormous sphere, the answer gets stranger. According to classical general relativity, a singularity. In practice, we expect that our current understanding breaks down there because singularities signal the failure of the theory at extreme conditions. A complete theory of quantum gravity may eventually tell us what truly happens. But for now, the black hole's interior remains one of the places where human physics reaches a cliff edge. We can describe the outside astonishingly well. The inside, beyond a point, becomes a frontier of ignorance. This is worth dwelling on for a moment. TON 618 is among the largest black holes known, and yet at its heart lies one of the deepest unanswered questions in physics. The bigger our telescopes get, the further we see, the more precisely we model, the more the universe rewards us with both understanding and mystery. Knowledge does not always end mystery. Sometimes it deepens it. That is why a topic like this can feel emotionally rich rather than just numerically large. There is a layered experience to it. First comes disbelief, then comparison, then some understanding of event horizons and quasar light, then a sense of how scientists infer these values, then questions about growth and cosmic history, then the realization that one of the largest objects of its kind we know is still, in crucial ways, not fully understood. The awe comes not just from the size, but from the combination of size, evidence, and mystery. And black holes have a way of sharpening philosophical instincts without needing any philosophical decoration. They force you to confront boundaries. Boundaries of space, of time, of knowledge, of survival, of language. TON 618 is so large that normal adjectives fail. At that point, science does not become less poetic. It becomes the only honest form of poetry left, because it lets the facts carry the emotion. Still, it helps to remain anchored. TON 618 is not a supernatural abyss. It is not an invitation to mysticism. It is a real astrophysical object studied by real methods. Its mass estimate comes from spectroscopy and modeling. Its luminosity comes from measured radiation. Its distance comes from redshift and cosmology. Its importance comes from how it fits into the broader framework of active galactic nuclei and supermassive black hole evolution. In other words, the wonder is earned. One thing many people instinctively ask is whether TON 618 could ever become larger still. In principle, yes. Black holes can continue to grow as long as matter falls in, and as long as mergers add mass. But growth is not automatic. Fuel can run out. Feedback from the quasar can heat or expel surrounding gas, making further feeding harder. Galactic environments change. Black hole activity often comes in episodes, not endless smooth meals. So TON 618 may have gone through intense active phases and quieter ones. The object we observe in ancient light captures one chapter, not the full story to the present day. Could there be even larger black holes out there? Very likely. At least candidates of comparable or greater mass may exist, especially in massive galaxies and galaxy clusters. Astronomy continues to identify ultramassive black hole candidates, though measuring the top end is difficult and uncertainties matter. TON 618 remains famous not because it is necessarily the absolute final boss of black holes, but because it so clearly occupies that ultramassive regime where the numbers become staggering. And the universe may have built some of these giants surprisingly early. That is one of the ongoing themes in observational cosmology. The early universe often seems more capable, more productive, and more structurally mature than simplified expectations once suggested. Massive galaxies appear early. Quasars appear early. Black hole growth appears aggressive. Every time we push our instruments farther back in time, the young universe keeps showing us a kind of reckless competence. TON 618, seen in the distant past, fits that pattern beautifully. It reminds us that the early cosmos was not a quiet nursery. It was dynamic, violent, and efficient at building complexity. At this point, it is useful to state the deepest takeaway plainly. The reason TON 618 feels so shocking is not just that it is large. It is that the universe can take something as conceptually simple as gravity and, given enough matter and time, create structures so immense and so extreme that they rival the scale of planetary systems, while remaining almost entirely invisible, except for the ruinous brilliance of what falls into them. That is a very different picture of reality than the one most of us grow up with. We begin life under one sky, on one world, with one sun. Space seems like distance and stars, but when you keep looking, you discover engines, traps in space-time, ancient lighthouses bright enough to outshine galaxies, dark centers around which entire histories unfold. And TON 618 is one of the places where the childlike idea of space is big matures into the adult realization that space is not only big, it is structured by extremes, and those extremes are not random spectacle. They connect to everything else. The black hole feeds on gas that could have formed stars. The radiation can shape the host galaxy's future. The galaxy lives inside a dark matter halo. The halo grew from fluctuations in the early universe. Those fluctuations came from conditions in the infant cosmos. So even a monster like TON 618 is part of a chain that leads all the way back to the earliest chapters of cosmic history. That interconnectedness may be the most beautiful part. The largest black holes and the faintest background radiation both belong to the same universe. The equations that help describe planetary orbits also help describe galaxies and black holes. Human minds, improbably small in the scheme of things, can trace these links. When you really sit with that, TON 618 stops being only a monster. It becomes evidence that reality is coherent across absurd ranges of scale. The same cosmos that made oceans and insects and trees also made quasars, powered by black holes wider than the planetary realm around our sun. One set of laws, one unfolding story, wildly different outcomes. There is something humbling in that, but also something energizing. Because every time astronomers identify an object like TON 618, they are not just cataloging a curiosity. They are extending the map of what nature can do. They are showing us that the universe is broader in possibility than intuition allows. And that is one of the reasons astronomy never gets old. No matter how much you learn, there is always another layer where the scale breaks open again. TON 618 gives us that experience in concentrated form. Start with a name that sounds dry and technical. Unpack it, and you find a black hole with tens of billions of solar masses, hidden inside a quasar, blazing across the universe. Keep going, and you discover event horizons larger than the planetary domain you call home. Keep going further, and you hit questions about relativistic gravity, cosmic growth limits, galactic evolution, and the early universe itself. That arc matters. It is the difference between hearing a fact and understanding a reality. And the reality is this: there are places in the universe where gravity has gathered itself into something so vast that our solar system becomes a useful unit for describing the size of the darkness. There are places where matter shines with the fury of trillions of suns, while circling a border from which no light can return. There are places so distant that when we observe them, we are seeing a younger universe already capable of building giants. TON 618 is one of those places. It reminds us that the universe is not scaled to human comfort. It is not built around the dimensions we find intuitive. Our brains evolved to judge cliffs, weather, faces, and distances across a field, not event horizons measured in billions of kilometers. And yet we can still reach toward these things. We can build instruments, decode spectra, compare models, and produce understanding strong enough to say, with justified confidence, that this object is among the largest black holes ever found. That should inspire a kind of sober wonder. Not the wonder of fantasy, where anything can happen because rules do not matter, but the wonder of reality, where astonishing things happen because the rules are deep enough to allow them. In the end, TON 618 is not memorable because it sits at the top of some cosmic leaderboard. It is memorable because it reveals a universe stranger than instinct, larger than language, and more coherent than chaos. A universe where darkness can be measured by the days it takes light to cross it. A universe where invisible gravity can ignite structures brighter than galaxies. A universe where one distant quasar can teach you that big is not really a size at all, but the beginning of a failed attempt to describe what is out there. So when you picture TON 618 now, do not just picture a black sphere with an impossibly large number attached to it. Picture a gravitational abyss with the mass of 66 billion suns. Picture an event horizon stretching far beyond the orbit of Neptune, if placed where our sun is. Picture light taking more than 2 days just to cross that dark boundary. Picture a quasar so luminous it announces itself across 10.4 billion light-years. And picture all of that existing not in a science fiction universe, but in the real one we already inhabit. That, more than any single number, is how big TON 618 really is. And maybe that is the lasting effect of meeting an object like this. It does not only tell you about one black hole, it resets the scale of your imagination. It reminds you that the cosmos is still full of things that can make even the most ambitious human comparisons feel small, and that understanding them does not shrink the mystery. It sharpens it. It gives it edges, numbers, structure, and meaning. TON 618 is one of the great demonstrations that the universe is not merely vast. It is extravagant in ways that are precise, measurable, and almost impossible to emotionally absorb all at once. The wider lesson is hard to escape. We live in a universe where ordinary stars can die into black holes, where galaxies can grow central engines millions or billions of times more massive than the sun, and where, in rare cases, those engines can become so extreme that their event horizons rival the size of entire planetary systems. That does not make human life meaningless. If anything, it makes knowledge more precious. In a cosmos this immense, every clear insight is an achievement. Every successful measurement is a victory against darkness, distance, and time. And perhaps that is the most moving contrast of all. TON 618 is a monument to gravitational power, a place where escape fails and light is trapped. Yet everything we know about it has come from light that did escape, from the inferno around the edge, from photons that crossed billions of years to reach us. We learned about one of the darkest things in the universe, because the universe itself left us clues. So the next time the night sky looks calm, remember that calm is only the surface impression of distance. Out there are objects like TON 618, ancient and colossal, feeding in brilliance around a center of absolute silence. Thank you for watching and for taking the trip. If you leave a comment, tell me where you are watching from and whether TON 618 feels more like awe or fear to you now. Until next time, keep looking up.